We are going to continue where we left off. This is Block 2 of Topic 2. Yesterday we talked about a scenario where we developed an equation that gave us the total bill for our cell phone. We used the variable t as a function of the variable m, where m is minutes and t is total bill. And here's the equation: t equals 0.07. This is $0.07, which is also 7 cents, times the number of minutes plus $10. So that was the plan. You pay $10 a month plus 7 cents a minute, which is really awful. Okay, so what we're going to try to do today is we're going to explore what happens when we change the equation so that it's no longer solved for t, so it's no longer solved for the total monthly bill. We want to solve it for the number of minutes. So we would use this equation if we had the number of minutes and we wanted to figure out the total bill. But if we knew the total bill and we wanted to solve for the number of minutes, we would have to solve for m. Okay, so we're going to talk about how to do that algebraically. Okay, so our equation looks like this. So we have a standard two-step equation. Okay, we have this decimal. It will be most convenient for us to remove the decimal. And it is a tenet of algebra that whatever I do to one side of the equation, I have to do to the other. So I'm going to multiply both sides of the equation by 100. Okay, the 100 will have to distribute over addition, so I'm going to have 100 times Okay, so 100t. And when we do algebra, we always want to rewrite our equation over and over. It seems like a pain, but it's the best way to avoid errors. So 100 times 0.07 is 7. 100 times 10 is 1,000. Okay, so now we have something maybe a little easier to work with. Okay, we're trying to isolate m. So now I'm going to subtract 1,000 from both sides. I'm going to skip writing If I subtract 1,000 from 1,000, there's nothing left. So this just remains 7m. Okay, now I've almost solved for m. The last thing that I have to do is to divide through by 7. Okay, so division distributes over subtraction just like it distributes over addition. So we're going to have to divide this by 7 and this by 7. And we're just going to leave it as fractions. Now I know as a student you like decimals. Mathematicians tend to use fractions. So we always need to be ready to work with fractions if we need to. Okay, so this is going to leave us with So now let's say we received our total bill and we wanted to know how many minutes we had used the cell phone for. Well, if our bill was $20, you would put 20 in for t. You would do 100 times 20 divided by 7, and from that you would subtract this quantity. And that would tell you how many minutes. Okay, so we found the inverse of the function. When you solve for the other variable, the function that you end up with is, for at least some of the domain, the inverse of that function. Okay, so let's talk about what do inverses look like. Okay, here I have a portion of the sine function and the arcsine function plotted. Now, the sine and arcsine, you saw them in geometry. They're trigonometric functions. They have inverses over a restricted domain. So we look at these two functions. The purple function is sine. It goes on forever. The blue function is arcsine. Now, if you look at this with respect to y equals x, which is the green line, you see that the functions are symmetric about this line. Everywhere that these are the inverses, they are symmetric about y equals x. All right, let's look at another example that may be easier to see. Let's look at y equals, all right, this is called the exponential function with the base of the natural log, and we'll learn about that more later on in the year. Okay, the exponential function and the logarithmic function, base e, are inverses. All right, let's look at their graphs. Oh, what do you know? They're completely symmetric because they're defined as inverses over all the positive domain everywhere that they are. So if you could tilt this view, you would see, it would be easier to see, but the blue and red graphs are completely symmetric about this function. If you were to fold this whole plane, this whole coordinate plane, along y equals x, these would line up. Okay, we're going to see that in a minute. Okay, so if we were to, just real quick, if we were to tabulate the data of minutes and dollars, and we were to switch their axes, hey, what do you know? It's all the same information, but we switch the axes. We put, here we had minutes in the x column, and t in the y column, and now we have the opposite. Okay, so later on during the class, you're going to recreate the solution to that linear equation. Okay, and you're going to put that information in to your student activity sheet. Okay, so when you come up with the right inverse of this function, they are plotted here. So here's the original function. It's a slowly increasing function. Here's its inverse. It's a rapidly increasing function. Turns out that their slopes are reciprocals. Okay, what this is saying is, hey, when you take this whole coordinate plane and you flip it, then you get this one. Okay, we're going to look at an animation of that here. Okay, we are plotting the original data along that line. So this is, the cost is a function of the number of minutes. Oh, we're flipping the axes. Now we're plotting the cost, the minutes as a function of the cost. we see they are symmetric about y equals x. Let's look at that one more time. Okay, so you should be ready to complete this activity sheet, and that's all.